Welcome, fellow traveler, to the realm of Bayesian Structural Time Series. Together we may journey where great Bayesian heroes have once tread. I can see that you have some training in time series and Bayesian statistics. This session will put these ideas into practice. In this chapter of our journey, we will encounter different implementations of the BSTS package written in R. This will include sea surface temperature data, model fitting of sea surface temperature, whose components include a local level, local linear trend, and seasonal trend. We will also generate a posterior distribution of our model time series. Lastly, we'll give some heuristic comparisons between different models. Again, the objective here is to implement the BSTS package. What's this here? It's a time series. This is our sea surface temperature data I mentioned earlier. The data displayed before us is temperature of the first 30 meters of sea in a region around Gibraltar off the coast of Spain. This is what our data looks like. Most of the temperatures lie between about 17 and 23 degrees Celsius, and there is obviously some seasonality here. Keep this in mind, however, we will first see how simpler models fare, and implement model complexity thereafter. The data is retrieved by Argo floats. Argo is an array of about 3,000 floats measuring temperature, pressure, and salinity of the top 2 kilometers of ocean globally. Here, the data is aggregated into 12-day periods from January 2004 to November 2017. I gathered this time series from the website ArgoViz. At argoviz.com, you can access data taken from instruments floating in the ocean all over the world. More information about ArgoViz is on my YouTube channel, provided by the link. Before we start fitting models, we need to do a little setting up. First, we load readr to read in the data, and of course, include the BSTS package. We read in the data, then convert it into a time series object. We set frequency to 30 because there are approximately 30 12-day periods in a year. The plot function produces the chart that we have seen in slide 5. To fit models using BSTS, we need to construct the state. Here, we call it LL_SS. We start by creating an empty list to hold our state specification. Then, we use the addLocalLevel function to say that we want to add a local component to our state. We then run the function BSTS, which generates the posterior distribution and fits our model. Along with our time series, we pass our state specification and we set the number of MC iterations to 1000. The BSTS function creates a model output object called LL_fit. You could think of it as a treasure chest of information. Let's take a look inside, shall we? After BSTS is finished running, we plot the results. BSTS provides several different plotting features. If we use plot with our BSTS object, what we get is a plot of the posterior mean conditioned on the data. The blue bubbles represent our original data. Specifying components in the plot function, we get a plot of the posterior of the state components. In this case, the local level. Based on this plot, it seems like the local level is doing a pretty good job of modeling the sea surface temperature data. We will see how wrong we are when we do some predictions based off of this model. Another option we can give to the plot function is residuals. BSTS also provides a predict method to compute forecasts. The horizon argument specifies how far ahead we want to forecast. In this case, we forecast 30 time steps ahead, which correspond to 1 year. To see how our forecasts are doing, we can pass our BSTS prediction object to the plot function. The plot.original argument plots the last 90 time steps of the original time series alongside the forecasts. The blue line indicates the median of the predictive distribution, and the green line indicates the prediction interval. The default is a 95% prediction interval. The gray shading displays the posterior density distribution. Take a look at those error bars. They look terrible. This model is saying that the sea surface temperature will most likely flatten out to around 18 degrees. I don't think so. Where's the seasonality? Surely we can do better. Perhaps if we introduce a local linear model, this will take into account these ups and down swings of falling and rising temperature. Let's take this monster on in another video, after we had a snack, and maybe a short rest.